velocity distribution here would be, excuse me, Vx over V infinite equals 2/3 times y times the square root of 13 over 280 times V infinite over nu times x minus 1/2 times y times the square root of 13 over 280 times V infinite over the kinematic viscosity times x to the third power. And finally, we can estimate the drag force. So estimate drag force. Where we see that the force as a function of x along that object would be 2 times the integration from 0 to w and the integration from 0 to L times mu times partial Vx partial y at y equals 0, so it's at the surface of the object, times dx dz, which equals to 1.293 times the square root of rho mu L w square over V infinite to the third power. Okay, so let's quickly kind of review using the von Karman's momentum balance to figure out the velocity distribution for a laminar flow flowing along a flat plate. So again, this would be our schematic here. So we have fluid approaching this, this flat plate with a velocity of V infinite. Once the fluid touches this flat plate, the boundary layer starts to form. Okay, so within the boundary layer you have a velocity distribution, but outside the boundary layer it's a potential flow. Okay, so based on our previous discussion, we can directly apply the von Karman's momentum balance, which looks like the following. And the key kind of like a trick, or the key idea here, is to make a proper guess of the velocity distribution. So the velocity along the x direction that distributes in the y direction. So v sub x of y. And a plausible guess would first be, it should be a function of y over delta, for which the delta here is the thickness of the boundary layer at any given x. Okay, and now we want to take a look at the boundary conditions, which help us to make a proper guess, right? So a plausible guess here with a reasonable shape. So the shape would be a curve like this. So it has to be, not just a linear relation, but at least second to third power. Okay. And so a plausible guess here is that Vx over V infinite would be 2/3 times y over delta minus 1/2 times y over delta to the third power. And why is this a plausible guess? Because first, if you look at the boundary conditions, first, it's satisfied that Vx equals to V infinite for y equals to delta. So when you're outside, so when you're at the boundary of the boundary layer, your velocity would equal to the potential flow regime. Okay. Also, it satisfied a no-slip condition. So when y equals 0 at the surface of the object, the velocity would be essentially 0. And also, it also satisfies one important key aspect here is that the velocity does not change anymore once it's outside the boundary layer. That means the gradient, the derivative of Vx over y, should be 0 at the boundary layer, and this also satisfies. Okay, so if you check that, if you take the first derivative of the guess, you see that indeed the slope becomes 0 when y equals to delta. Okay, so this is a very nice guess to start with. It satisfies all boundary conditions. Now let's substitute this guess into the von Karman equation and try to solve it. And that's what we're doing here. So we've substituted into the von Karman equation and we get the following. We get that the left-hand side equals to 2/3 times mu v infinite over delta x equals to the first derivative of what's inside this bracket with respect to x. And this is a very relatively simple separable first order ODE. So you just need to shift the terms on both sides to integrate both sides, and then you should be able to figure out that delta x equals to the square root of 280 over 13 times the kinematic viscosity times x over v infinite. So it would be 4.64 times what's in the square root operator. And having the delta x distribution, we can now substitute this back to our initial guess for velocity, right? So we can go back and put this back here. So now we get the velocity distribution. We get the velocity distribution down here. And finally, we can get the drag force by using what's on the left-hand side of the von Karman momentum balance. Okay, so basically, you're just integrating that term with respect to x and z, covering what? Covering the lateral dimensions of the object. Okay, and that gives you this estimation of 1.293 times what's in the square root operator. Okay, so trying to finish our previous example, and now we're going to head into a new contents for today. So today, let's try to type this. Give me a second. So today is actually 2022, May 30th. And today we are going to look at boundary layer theory for non-isothermal flow. Okay, so the title for today's topic would be Boundary Layer Theory for non-isothermal flow. Okay, so again, we will try to consider a two-dimensional flow around a submerged object. Again, in the vicinity of the solid surface, the equation of changes would be the following. So let's try to write this down. So we're going to consider a two-dimensional flow around a submerged object. Okay, so in the vicinity of the solid object, or let's say the solid surface. The equations of change would include the following. So the first one would be the equation of continuity. So again, we have partial Vx partial x plus partial Vy partial y equals to 0. Then we should have the equation of motion. Okay, so the equation of motion is the density times Vx partial Vx partial x plus Vy times partial Vx partial y equals to rho times V from the potential flow times dVe dx. So this is, you remember, this is from the potential flow. For potential flow and plus the drag force, so mu times partial square Vx partial y square. And now, because it's non-isothermal, we are going to put in the buoyant term. So rho gx times beta times t minus t infinite. Remember that from our previous discussion and derivation, we know that we just need to focus on the x direction, right? So the contribution, or let's just say this is based on order of magnitude analysis. The equation of motion in the x direction has orders much greater than in the y direction. So we are only considering what's happening in the x direction, right? So this is like an extension of the Prandtl momentum balance or the Prandtl boundary layer equations, except that we are introducing the term for buoyancy. And finally, let's take a look at the equation of energy. So equation of energy. So we have rho Cp times Vx partial t partial x plus V sub y partial t partial y equals to the thermal conductivity times the partial square t partial y square plus mu times partial Vx square partial y square. Okay, so this would be our equation of energy, and in most cases during our discussion, we will assume that the density, the viscosity, the thermal conductivity, and the heat capacity are constant. And in most cases, when you're very close to the solid surface, and in most chemical engineering cases, we will disregard the viscous heating term. Viscous heating term disregarded in most cases. Okay, so once we have disregard the viscous heating term, so now we have solutions, and we can solve for the solutions. And here are some important properties of the solutions we want to plan out first. So the solutions are asymptotically correct, asymptotically accurate for small momentum diffusivity. So the momentum diffusivity is actually the kinematic viscosity, so it's going to be the viscosity over density. And for small thermal diffusivity, the definition of thermal diffusivity will be alpha equals to the thermal conductivity over rho times the constant pressure heat capacity. Okay, so the solutions are asymptotically correct for small momentum diffusivities and small thermal diffusivities. And then another important thing for the non-isothermal flow is we are including the term for buoyant force. So it's on the inclusion of buoyant force term in the equation of motion. Okay, so again, for non-isothermal flows, we will have equations of change, including the equation of continuity, the equation of motion that now includes the buoyant forces, and the equation of energy, which in general we will neglect viscous heating. Okay, and with the equations of change established, let's take a look at the boundary conditions. Let's look at boundary conditions. So we will adopt a lot of these from the momentum balance part. First is we know that there are still no slip conditions at the boundaries. So Vx equals Vy equals 0 at solid surface. 2, velocity approaches the external velocity, or we call it the potential flow at outer edge of the velocity boundary layer. So an important term here is we are saying one thing as velocity boundary layer. This is a key point that will come back. And then 3, we have temperature would equals to some T naught at solid surface. And 4, temperature equals to some T infinite at the outer edge of the thermal boundary layer. Okay, so you see that we have two terms for boundary layer. Now we have a velocity boundary layer and a thermal boundary layer, and these two are not necessarily the same. So the question we want to ask here naturally would be, are the velocity, or do these two boundary layers share the same thickness? Right, so the question would be, are velocity and thermal boundary layers sharing, or just say the same in thickness? How do we answer this question? Well, basically, again, we will kind of come back to some dimensional numbers or dimensionless numbers. Basically, it's determined by the relative ease of diffusion of momentum versus heat. So if momentum diffuses faster than heat, then you would have a thicker velocity boundary layer. So determined by relative ease of diffusion of momentum and heat. Okay, so basically, what is the measure of the relative ease of diffusion of momentum and heat? The answer is something that you already are pretty familiar with, which is the Prandtl number. So the Prandtl number, abbreviated PR, which equals to what? Equals to the kinematic viscosity, which is the momentum diffusivity over the thermal diffusivity. And we can take analysis here. So for Prandtl number greater than 1, the temperature boundary layer usually lies inside the velocity boundary layer. For Prandtl number smaller than 1, the relation would be reversed. Okay, so that means when momentum diffuses faster than the thermal diffusion, okay, then the temperature boundary layer will lie inside the velocity boundary layer because it does not penetrate that far. And when Prandtl number is smaller than 1, the relation would be reversed. So as a reference, the Prandtl number equals to about 3/4 for gases, and the Prandtl number would be much smaller than 1 for liquid metal. Okay. Now let's keep our discussion. keep moving on our discussion. So remember that for the velocity boundary layer, we used the integration from y equals 0, equals to 0, to y equals to infinite to obtain the von Karman momentum balance. And we did that using the equation of continuity. So here, similarly, we are going to do the same type of trick to acquire the von Karman momentum and energy balance. So again, this would be an approximates boundary layer solutions. So we have the von Karman momentum and energy balance. So let's take a look at the momentum first. So momentum, we have again mu times partial Vx partial y at the solid surface, y equals 0, equals to d dx times the integration from 0 to infinite rho Vx times V sub e minus V sub x dy plus d V sub e dx times the integration from 0 to infinite rho times V sub e minus V sub x dy, and then we have additional term for buoyancy. So again, integration from 0 to infinite rho g beta times t minus t infinite dy. Now let's take a look at the energy equation. So energy, we have the thermal conductivity times partial T partial Y at Y equals to 0, again at the solid surface. So the thermal conduction at the solid surface equals to d dx times the integral from 0 to infinite rho Cp V sub x times T infinite minus T dy. Okay, so the von Karman momentum and energy balance, these equations are valid for force and free convection, and also the no slip condition always applies. So no slip condition at y equals to 0. Okay, so now let's take a very similar look at a very similar example as we did before. So, example. Let's take a look at heat transfer in a laminar forced convection along a heated flat plate. Okay, so we are again using the von Karman integral method. Okay, so again, we have, let's draw some schematic first. So we have a flat plate. It's not that flat. Let's try to make this better. So flat plate. Like that. And then we have incoming fluids. Okay, the incoming fluids with V infinite and T infinite. And as the fluid touches the front end of the plate, a boundary layer is starting to develop, which we have two kinds of boundary layers now. We have the velocity boundary layer and maybe a thermal boundary layer. So the blue refers to the velocity boundary layer, and the red refers to the thermal boundary layer, for instance. Okay, and the plate is maintained at a temperature of T0. So the question, or we know that, if we look at the velocity profile, it should look like this and becomes flat outside the velocity boundary layer. And then we also have a temperature gradient that might look very similar. Okay, so outside the boundary layer, T equals T infinite, and outside the velocity boundary layer, V equals V infinite. Okay, so our first step, which we've just done, is to postulate reasonable forms for the velocity and temperature profiles. So what that means is we've done this on a graph. Let's try to do this, with some equations or mathematically. So what that means is that we can divide two stuffs here. We know that the easy part is when we are outside the velocity boundary layer, so at y greater than delta of x, or greater than or equal to, we know that the velocity with respect to the V infinite would be the same, so it equals to 1. But when you're within the boundary layer, we can postulate something like Vx over V infinite equals to 2y over delta minus 2y over delta cubed plus y over delta to the 4th power. Let's try to write delta better. Okay, so we have, if you look at the boundary condition, so that means that Vx over V infinite equals to 0 at the wall and equals to 1 at the outer edge. And let's take a look at the first derivative of this equation here. So if you take the first derivative, so Vx over V infinite to the first derivative, we now have what we now have 2 over delta minus 6 over y squared over delta cube plus 4y cubed over delta to the 4th power. And this would equal to what? Equal to, when y equals to delta, this equals to 2 over delta minus 6 over delta plus 4 over delta, which equals to 0 again. So yes, it satisfies the partial Vx partial y equals to 0 condition at y equals to delta. So this would be a reasonable guess, and that for the velocity distribution, and that, you know, satisfy all boundary conditions. Now let's take a look at the temperature distribution. So again, we'll divide this into two cases. So at y equal or greater than the thermal boundary layer, we have T naught minus T over T naught minus T infinite equals to 1. So the dimensionless temperature equals to 1. And at y smaller or equal to the thermal boundary layer, we have T infinite minus T over T infinite minus T, sorry, T naught minus T over T naught minus T infinite equals to, using the same form, we have 2 y over delta T minus 2 y over delta T cubed plus y over delta T to the 4th power. Okay, and you can see that they would all agree with the same set of conditions. So the key here is we're actually assuming the dimensionless velocity and temperature profiles have the same form within their respective boundary layers. And also we will have another assumption. We would let's further assume that the ratio between the velocity and thermal boundary layer is constant. And that value equals to delta T over delta is smaller or equal to 1. And now you see that we have the velocity profile, or the guess of our velocity profile, and the guess of our thermal or temperature profile, which are, you know, already fulfilling the boundary conditions. Our next step would naturally, again, be substituting these equations or these guesses into the equation of changes, right? So for the velocity one, we're going to substitute into the equation of motion. And for the temperature profile, we're going to use it for the equation of energy. Okay, so putting that down into words, that means we are going to substitute plausible guesses into von Karman momentum and energy balance. So this is something that's straightforward but pretty tedious. Straightforward but tedious. Now we're just going to show you the results. The results are the following. First, let's look at the momentum balance part. So we have the following relation. So the integration from 0 to infinite times rho Vx times V infinite minus Vx dy. This now equals to rho V infinite squared times delta of x times the integration from 0 to 1 times 2 eta minus 2 eta cubed plus eta to the 4th power times 1 minus 2 eta plus 2 eta cubed minus eta to the 4th power d eta, which now equals to 37 over 315 times rho V infinite squared times delta x. And also for the energy equation, we have integral from 0 to infinite rho Cp Vx times T infinite minus T dy equals to rho Cp V infinite T infinite minus T naught times delta T of x times the integral from 0 to infinite times 2 eta sub t times delta minus 2 eta cubed sub t times delta cube plus eta cube t delta 4 power times 1 minus 2 eta t plus 2 eta t 3rd power minus eta t to the 4th power d eta t. So this now equals the following, equals to 2 over 15 times delta minus 3 over 140 delta cube plus 1 over 180 delta to the 4th power times rho Cp V infinite times T minus D infinite minus T naught times delta T of x. Okay, and here the eta equals to y over delta. Eta sub t equals to y over delta sub t and equals to y over delta of x. Okay, so once we have these, again we will substitute into von Karman balance and solve the first order ODE. Separable ODE. To get the following. So we now have the solution for delta x equals to the following. It equals to 1260 over 37 times the kinematic viscosity times x over v infinite. Let's call this equation 1. And then the thermal boundary layer, so delta sub T of x equals to 2 over 15 capital delta minus 3 over 140 cube of capital delta plus 1 over 180, the fourth power of the capital delta times alpha, thermal diffusivity, times x over v infinite. Let's call this equation 2. Okay, so we have the velocity boundary layer and the thermal boundary layer figured out, or estimated. Now let's take a quick look at the capital delta. So now let's evaluate the capital delta. So what we're going to do is we're going to divide equation 1 by equation 2. So we have the following relation. So 2 over 15 times the capital delta minus 3 over 140 capital delta, this cube 5 plus the 6th power over 180 equals to what? Equals to 37 over 315 times the inverse of the Prandtl number. Here, the capital delta is equal or smaller than 1. Now we can solve this. So solve this 6th order polynomial, or algebraic equation of the capital delta as a function of the Prandtl number, and the solution may be curve fitted by the following equation. So the capital delta now equals to the negative 1/3 power of Prandtl number when the capital delta is smaller or equal to 1. And this is pretty accurate, within 5%. Okay? So finally, let's take a comparison between the boundary layer heat transfer calculations for flow along this flat plate. So above we are looking at the von Karman, and now let's look at the actual values obtained from numerical methods. Okay, so let's say this would be a comparison of von Karman. Let's call that approximation. And exact solutions. So here we go. So we see that from the von Karman method, the value of numerical coefficient this is square root 148 over 315. So it's about 0.685. And based on the exact solution, by this person, we have 0.657 at Prandtl number equals 0.6, 0.664 at Prandtl number equals to 1, 0.670 at Prandtl number equals to 2. So basically, the von Karman approximation is within a relatively good agreement, and so coming back to what we have obtained here. So with the velocity and thermal boundary layers obtained, we can now try to really figure out the temperature and velocity distribution. Okay, and let's look at the temperature profile. So the temperature profile we have T naught minus T over T naught minus T infinite equals to 2 y over capital delta delta minus 2 times y over capital delta delta to the third power plus y over capital delta delta to the fourth power. And we have the assumption for laminar flow, right? So we will give you the limits for that. So the assumption of laminar flow is valid for x smaller than the critical x, where x critical times v infinite times rho over mu is usually greater than 10 to the fifth power. And finally, we can look at the rate of heat loss from both sides of the plate. So rate of heat loss from both sides of the plate, which would be the following. We have Q, which is the heat transfer, equals to 2, so two sides, times the integral from 0 to W, so these are the lateral dimensions of the plate, times Q of y at y equals to 0, dx dz. And this equals to 2 times integral 0 to W, 0 to del, rho Cp Vx t minus t infinite at x equals L times dy dz. And this is based on the von Karman energy balance. Okay, and let's proceed. So this equals to 2w rho Cp v infinite t naught minus t infinite times 2 over 15 capital delta minus 3 over 140 capital delta cube plus 1 over 180 capital delta fourth power times the thermal boundary layer as a function of L. So this would be approximately the square root of 148 over 315 times 2WL, the lateral dimensions, times T naught minus T infinite times K over L times the 1/3 power of Prandtl number times the square root of the Reynolds number. Okay, so we have plenty going on. Let's try to go back and, organize our thoughts again. So again, let's start from the flat plate argument here. So remember that after we have derived the von Karman momentum and energy balance, we're going to use that to look at a simple example, which is heat transfer in a laminar forced convection along a heated flat plate. Okay, so again, you have a heated plate at a temperature of T naught. You have incoming flows with temperature and velocity of V infinite and T infinite. You would develop two types of boundary layers, one for thermal, one for velocity. And we will assume that basically the thermal and velocity boundary layer have the exact same type of shape, except that they have different thickness. So the ratio between these two is going to be assumed constants. The ratio between the two boundary layer thickness is assumed constant. So they will have the same type of formulation, which satisfy the boundary layer conditions, the boundary conditions at no slip condition, and also being equal to the potential flow at the edge with a zero gradient at the boundary layer. Okay, so basically after having these suitable guesses, we're going to substitute them into the von Karman momentum energy balance. It is straightforward but tedious, so we're just going to show you the results, and the results are basically down here, which is the velocity boundary layer equals to equation 1 down here, and the thermal boundary layer as a function of x equals to equation 2 down here. Okay, and as a side note here, we're actually trying to show you some analysis on the capital delta here, which is basically the ratio between the two boundary layer thicknesses. And it's actually, the key point is that you can actually estimate that ratio using the negative 1/3 power of the Prandtl number, provided that you know that the ratio is equal or smaller than 1, meaning that the thermal boundary layer is lying within the velocity boundary layer. And this gives us quite good accuracy within 5%, and that can be further justified by looking at the comparison between the von Karman solution versus the exact solution here. You can see that the coefficients are fairly similar in their magnitude or orders. Now, having the thermal boundary layer figured out, we basically will substitute that back to our guess for the temperature distribution. That's why we now have the temperature profile written down here. Okay? And having the temperature profile figured out, we can now try to, determine the rate of heat loss from the plate to the fluid, which only happens in the boundary layer, because outside the boundary layer, there are no more temperature distributions. Okay, so let's probably take a break here, and we will come back later looking at a very similar problem, except that we're looking at asymptotic solutions for large Prandtl numbers. When Prandtl numbers are large, that means your velocity boundary layer is much thicker than the thermal boundary layer. And once that happens, things get a little bit simpler. We can actually assume something quite simple in terms of the velocity distribution that simplifies our analysis. But we'll come back to that later, and we'll take a break here.